And you know where the lab or
Welcome for another graduate student seminar series. This week we have Noah Berkowitz, who's a PhD candidate with advisors Dan Udin and Brian Wardlow. Noah is a PhD candidate in geography from the New York, New Jersey area. His research utilizes remote sensing data and geographic information systems analysis to investigate dryland corn agriculture in Nebraska. He collaborates with the United States Department of Agriculture and several private entities to explore issues related to crop yield, profitability, and the dynamics of agricultural land use change. So today, Noah will be talking to us about advancing precision and farmland segmentation, open source methodologies, and applications. So I'll go ahead and turn it over to Noah.
I wish I could just sit in the chair. But no. So yeah. Kind of an informal presentation I wanted to give. It's kind of a backwards presentation in terms of how it's functioning. It's not really research. It is research driven, but not in the way that a lot of these presentations are. So my presentation is about farmland segmentation, applying open source methodologies and some of the applications that go along with that.
Yeah, I think my office with that, and it's hard to.
Last time I think you had to scroll.
Oh. There we go. Okay, so Nebraska is an agrarian state, as most of us are aware. It has over 2.5 million dryland acres in production, and when we're talking about dryland acreages, they're non-irrigated. Although Nebraska is primarily associated with the center pivot agriculture when it comes to corn production, I focus in on dryland production, particularly in the MLRA area. And I'll go on to explain a little bit more what that actually is. The MLRA is the major land use area. It's an agroecological region. Our particular region that I focus on, which includes Lincoln as well, is MLRA 106. It's over 429,000 acres. Of the original prairie in the MLRA, 62% has been converted to agricultural use, and with only around 23% varying from year to year, of course, remaining as intact grasslands, soil types of pawnee and escarpment. 25 to 30% of Nebraska's total agricultural acreages, as also including pastures, is considered as corn. 85 to 95% of that corn is managed within a corn and soybean rotation predominantly. So one year's corn, the next year is soybean. When we're talking about segmentation, what do we actually mean? It's basically lifting a physical spatial attribute from a specific area. What you're seeing right here is rice fields in Ecuador. This was a part of my master's project. It's Sentinel SAR data, and we're using a couple of algorithms and thresholding to lift out those very ponded rice fields in the coastal region in Ecuador. So our area of interest, of course, is MLRA 106. The state is broken up into numerous MLRAs. Ours drops all the way down to almost Kansas City and Topeka, and goes all the way up to almost the Omaha and the Omaha metropolitan area past. So the goal overall of my talk today is basically explaining chapter 1, and what that's including is understanding the size and shape of croplands. And that's vital towards yield estimation. I'll explain later on. My goal of chapter 1 is to calculate yield for this area and apply open source platforms and frameworks in a publicly accessible manner. Fill data gaps as well. Data sources exist like the cropland data layer, but none can solely identify dryland cornfields. Sources also don't purely segment individual fields, as in you want what I would describe as a bounding box. You really don't get those neat bounding boxes using these data sets. And also there is a clear lack of publicly accessible of in situ or ground truth data, as in farmland specifically driven data. The chapter workflow. So this is my chapter 1. We're focusing in just on that center part of chapter 1, that overall segmentation. Segmentation is applied to a production efficiency model. And what is a production efficiency model? It's a semi-empiric model that is used to calculate usually biomass or some sort of carbon refuse. In this case, we're calculating corn yield. In terms of open source applications, we're using the Google Earth Engine API in Google Colab. It's also written in the Anaconda Cloud. If many of you are familiar with a lot of the platforms like Spider or RStudio or Jupyter Notebooks, a lot of them are driven from the development of Anaconda. I use that base development known as Anaconda Cloud to host this huge calculation that occurs across hundreds of thousands of fields. Data is applied from open source catalogs. So I use the awesome GEE catalog, the awesome Google Earth Engine catalog, and Google Earth Engine's own catalog to apply the data sets. All those data sets follow a stack, which is a spatial temporal asset catalog. That's a clear and open source formatting for how data is supposed to be cataloged and represented online or distributed as well. This data set itself is cataloged within Stack 1.1, which is the latest metadata formatting for that open source asset catalog. Regarding methods, the USDA NAS dataset, i.e. The CDL, the cropland data layer, was selected as a general base layer to understand the cropland cultivar and the size. The landed data set was masked to the CDL to remove all the dryland fields. The NAS CDL and the landed data set suffer from fragmentation effects. So what does that mean? Basically is you'll see erroneous data applied across any sort of space. Generally pixels showing up where they shouldn't be, or erroneous field shapes and sizes, or a field classified smaller than it should be, but it's still a field. So how did we get around that? We applied a weighted generalization algorithm to evaluate the segmented field size and remove anomalously small and fragmented fields. So applying a weighted window across the MLRA to understand what's the average field size for a given area, and then excluding anomalously small fields or fragmented fields, and then grouping them back into said field that might be within a N space next to that pixel. This dynamically adjusts across the MLRA for best fit and field size and given abutments. It's generally based on a k-nearest neighbor algorithm and a weighted formula to understand potential size and infill gaps. In situ data was applied to revise the algorithm on top of the dynamic adjustments and to understand producers' accuracy and users' accuracy. Some of the general results. The refinement has produced decrease around 6.73% across the MLRA counties. That results in almost 100,000 acres per county in general reduction of size from the CDL. This is a given published data set, so reducing the data set in a singular county by 100,000 is a massive amount. And when we're talking about 100,000 acres, that could be across 20 years, 1 million bushels of produced corn. So affecting yields estimations is incredibly redefined by this refinement. So some accuracy, map accuracy assessments. I don't know if a lot of you are familiar with area under the curve or producers accuracy, but they're relational map accuracy assessments. So if you have X and X, how does that relate? Or if the user is looking at X and the test sample is X, how does that actually relate in an accuracy assessment? So we're receiving actually government standard for map accuracy is around 83 to 85%, and users accuracy, we're at 86%, so that's above the given rate. Producers accuracy is at 81%, and area under the curve is 83%. In general, these values of course represent non-irrigated data sets. Irrigated corn acreages are minimal in this MLRA. As we know, Nebraska is dominated by the center pivot agriculture. So they were excluded in the original USDA NAS reports, and what I mean by that is USDA collects NAS statistics. NAS statistics are ground truth statistics, but those are generally given actually for combined corn, combined dryland and irrigated data sets. So we couldn't use NAS. What we were using was the CDL. This accuracy was assessed on CSP3, CSP1, and also a data set from Indigo AG, which is a carbon offset company. They provided me with spatially segmented fields that were representative of ground truth GPS data. So when getting into the actual results outside of the accuracy assessments, we're seeing a largely increasing trends across 20 years of the dryland corn acreages. Why are we seeing that? It's largely because the ethanol boom in the mid 2000s, and then in the spring a dip in 2019 due to exceptionally wet conditions in this MLRA, and then a roughly 1 million acreage increase from early 2000. A little bit of a conclusion is overall the average dryland cornfield size grew from around 80 acres to almost 103 acres, and this is individual field size. The farm range in Nebraska is growing as well, hitting around 956 acres in this MLRA across the 20 years. Of course, illustrating a trend towards larger fields, as a lot of us are aware that farmlands are consolidating and a shift towards a larger scale and larger efficiency. Also, the incentives are driven towards consolidation as well. Larger fields often mean less habitable lands, and of course, more significant erosion on sloped areas if the terraces are removed, which they are in this type of agriculture. So a quick application side. All this data is organized in an open portfolio that is almost done on ArcGIS Online and also hosted in a Xavia stack format. That is a clickable portfolio of every single field. You get the soil type, the yield, the field size, field change, yield size, yield change, a general PCA for every single field, a principal component analysis, weighted averages, and then you're able to compare what the generalized biomass was from the Montana Terrestrial Dynamics Group, NAPE NDVIs, and generalized Sorgo data back to NCCPI, which is the National Commodity Crop Productivity Index, which is a weighted index for productivity based on how potentially productive that soil might actually be. And this is generally what the prototype looks like now. Of course, it will be expanding, but every single year we'll have maps and across the well over 200,000 plus fields. At each 30-meter pixel will be, or is right now, clickable to view that information. So this is kind of really what I wanted to talk to you about, but I'm just saying, hey, I want to talk about OSM or Overture Maps Foundation without actually talking about my research is probably frowned upon. So some of my passions are the open source data sets and the organization of open source data sets and how are we sharing open source data sets. The oldest, biggest open source data set is OSM, that stands for OpenStreetMap. I'm pretty sure all of us have used OpenStreetMap without actually knowing what it is. If you've ever used Apple Maps or Bing Maps or Facebook or Snapchat Maps, you've used OSM. OSM is considered widely as the Wikipedia for maps. It is a mapping foundation that provides a base map to, I would say, 90% of all of corporate America. It is one of the most accurate base maps out there. Coming out of OSM, a group of corporate entities realized Google's and Apple's dominance in the mapping field. A lot of us use Google Maps. Inherently, they ruled a monopoly. Overture Maps Foundation was created to build on top of OSM's work, but gather the largest companies in the room that use OSM but don't really redefine what is actually that data looking like, to gather them in a room and build a better data set. And Overture Maps was the result. Overture Maps is a conglomerate of Facebook, Microsoft, TomTom, all of the big companies you could possibly think of that put together maps, creating a singular base map for the entire world. This is humanity's most accurate map ever created. It is publicly accessible, it is easily downloadable, and it is open source, shockingly. Why am I bringing this up? That's probably a question that a lot of you are interested about. One of these things that are these maps, these two maps that feed off of each other is missing is farmland data. If we just scrolled to an area in Scribner or Valley or Norfolk, you would see absolutely nothing on their base map. So one of the things that I've been working on is creating a base map for this area called the Farmland base map of this, I want to call it like the Farmland base map of Nebraska. I haven't come up with a name yet, but one of the important things that I'm working on is the inclusion of farmland data in OSM. So one of the things that we'll start seeing is in this area is the drawn layers just popping up for farmlands. It's kind of important when it comes to the inclusion of these data sets because when you just zoom into Nebraska, you most of the time don't really see anything when you're looking at these maps. If you zoom into an area on Google Maps, you won't see anything. So changing that has been a goal of mine and I think should be a goal of a geographer in this field. Another thing that this is kind of the background of it all is HOT OSM. HOT OSM is Humanitarian OpenStreetMap. Humanitarian OpenStreetMap is a project by the OpenStreetMap group that culminates mappers and developers and humanitarian organizations to work on different projects that may have either tied to disaster or development or an aid project. It's a totally open source platform that anybody can contribute. I would really encourage people to contribute. The reason why I want to give this presentation is with the lack of US aid organization, things like this really become valuable, platforms like this really become valuable. And the need for people to contribute just basic mapping needs, whether that's actually segmenting a farm field or segmenting a house or a building or anything in disasters really is super evident and needed. And the most amazing part is you're directly contributing to aid projects, as we could see one listed right here. And you could see the organization descriptions, the impact. you could, and it's also teaching you more GIS skills doing this type of work as well. It's really important to me, and that's kind of the only reason why I wanted to do this talk was HotOSM. They've lost some of their funding with USAID. So if you could just contribute a little bit of your time, they don't really ever request any money to help out any one of the projects. I want to start a team, but they've really locked that feature. You can add me as a friend, that's my username. Please do, but if you can, or if you have the time, check it out. The goal is really just to help people out, and it's a valuable pursuit. That's sort of it. It was a quick presentation, only really had one goal. I do work a lot with Google. This is built off of Google Earth Engine. I'm in a bunch of groups with them, in the Geo Practitioners group or whatever. They have really amazing conferences and they offer funding for them. And if you are not able to get the funding, the conferences themselves, at least the travel funding, are free, and everything when you're at the conference is paid for. If you're interested in applying, please do, or let me know what that application process looks like, or how to frame your application. It's a really great event that ties a lot of developers in the open source field together. And also they do give a lot of platform-based credits too, whether it's their AI platform, their server platform, or just general access to unlimited Earth Engine. I really recommend going if you're doing this type of work, just because of the benefits provided. And they also will sit you one-on-one down with a developer on that team and really dig through your project and see where your code needs to go and how to help you. They have one coming up in New York City, and you also get to go to their campus like that. In their New York City campus or their Singapore campus. They also have one on their Mountain View campus in California, and also in one of their offices in Brazil. They may have some more that I'm not aware of, but let me know, and thank you for your time.
There's be plenty of time for questions, yeah, so if anyone has any questions for Noah, go ahead and start asking, and if Noah, if you could repeat the question to the people on Zoom, so they can hear too, but yeah.
I've got a question about the segmentation methods. It seems like they work really well for farmland layers or cropland layers where you have pretty homogeneous environments with distinct boundaries, right? If you look at like an aerial image of croplands, it's pretty clear what is agriculture and what isn't. How well do these segmentation algorithms work in natural ecosystems where boundaries are much more fuzzy and you have more diversity?
So it's a great question. Segmentation itself has grown by leaps and bounds over time. Platforms overall, first I'd like to answer your question as in, don't buy the hype when you hear these things. There's algorithms out there like from Meta's group and that apply data into OSM called segment anything, that they literally believe that through algorithms they could segment anything. While that might work part of the time, it is hype. What I would say to answer your question overall is highly parameterized algorithms work well better in natural environments. This algorithm itself is derived off of the CDL, which is very homogeneous. But one of the more important things is the cover itself is not homogeneous within the CDL. So there's all different cultivars that the CDL tries to classify, but what they do is they tweak that algorithm accordingly. One of the biggest projects actually that I've been involved with in terms of tough segmentation in natural environments is this one. In Ecuador, mangrove lined forests. So covering how do we segment things in semi-saline or aka brackish ecosystems that are tree-lined? Well, looking for different sensors like SAR is actually an option because of their ability to cut through heavily clouded Ecuador. This region's at elevation, so cloudiness level in a rainforest is exceedingly high. So using regular, remote sensing, panchromatic remote sensing is not an option here. So you would need to use other sensors as well. So one of the things is using other sensors like SAR is definitely an option. So synthetic aperture radar that can really meet the goals of what you're trying to do. If you're focusing on very wet environments, and also tweaking your sensors and having refinement in the data sets itself is, I think, something that's key to kind of getting towards that nature-based answer. Hopefully I answered the question.
About OSM, so I really appreciate that you're working on that. I've also worked a little bit on OSM stuff. Yeah, and one thing I think you might already know it, like you can do a mapping party. Back in the days, we used to do mapping party with either trains or registrants and to map the areas that were not mapped. And it's your, I really appreciate your report on that. And the other question is, because you talked about the precision agriculture and I guess and also the open source software. So the first question is like your thought on how you use Google Earth Engine, some other open source libraries, and then you come up with the ArcGIS online to visualize it. What's your thought on that? Because Google Earth Engine, although they claim it's free for educational purpose, it's not really free. And ArcMap or ArcGIS online is not free at all.
Yeah, this is a great question. So one of the problems is, as when you scale data sets, the need for compute increases. So Earth Engine provides a scalable platform along with Colab that could easily scale elastically as compute need increases. While the platform itself and the API in the back of that, i.e. whether I'm running those algorithms or how is these algorithms hitting the computer, are open source. They are technically paid at this scale. I'll 100% admit to that. That is a downfall of these types of calculations. AGO was selected because of the university has credits, so hosting is free. That's sort of the main problem with these types of projects. Even in my master's, I was on a team called the Mapping Africa Project. Please look up their GitHub if you're interested into the Mapping Africa project. Super awesome project. The main problem there was the hosting got so expensive with AWS and S3 storage that they really had to look towards other means. So one of my main problems is I can't store on a Calmet server or Swan or things like that just because of the immense size. And the need to compute itself and the structure of that would actually incur a larger cost using our own university resources on site. So it is open source, but it is paid because of the immense need of resources. At the end of the day, the code, the data is all open source.
And one more.
Please.
So because I guess you use NSAT for delineating those areas, right? So how does that affect the accuracy of the area estimates? Because for precision agriculture, there might be need for higher accurate boundary?
So, CDL is a Landsat derived, and now Landsat and Sentinel as of 2025 calculation. And as of 2025, it's actually 10 meters. It's a refinement on that data set, but in the past years, since I was calculating since 2001, it is at 30 meters resolution. 100% that a higher resolution data set would mean higher results or a higher fidelity in the results. But one of the other problems is just scaling at this size becomes very, very difficult, where we're already at 7 terabytes of data in 1 year. So when we're talking about 20 years, we're gonna get over 100,000 gigabytes of data. Just in the calculations itself and for the yield in that first chapter, and then the segmentation. So the problem is definitely balancing resolution and resources. One of the things that I have done and have gotten access to and recommend other people try out is Planet has a graduate student, I think they still have it, program where you can acquire their imagery. Have acquired 5-meter imagery from Planet with their Super Dove and earlier Dove satellites, and worked out the same calculations with them. It's just so intensive in terms of the compute need that later on in this project, I decided that it wouldn't be necessary. The ground truth data is GPS-based producer data. So it's referenced at this the highest resolution possible. It's combine-based data. So although it's at 30 meters, it's referenced at the combine.
Thank you.
Are there any other questions?
Where do you see this technology being in 5 years?
5 years.
That's a long time.
I don't see, like, with the cyclical cycle of administrations and funding, I don't see NASA really evolving as fast as their benchmarks actually state. The Landsat satellites have notoriously been not on time by a matter of years. So the need for higher compute increases, but I think the evolution is actually in the generalized algorithms. So Planet has collaborated with OpenAI to basically create a segment everything where I could basically they're gonna unveil a product in the future that I could just type in how many rain-fed cornfields are in Escarpment, Nebraska that were marginal across 15 years. That type of calculation in the next 5 years will be done. That's the type of work that I do as a PhD. So it's kind of maddening and frightening to think that, like, there's literally demos by these companies right now to show that off. I do think that these companies will increase in resolution. But the access to them, I think, will always be the trend, that they'll always be like subscription based and a high cost as well. Yeah.
You talked about integrating crop fields into the open map software,
Yeah.
OpenStreetMap or something. Could you highlight the importance of why?
It's a great question. So my overall idea with that integration is the fact that, one, having it in these platforms outside of something like Zendodo or like the publishable scientific sphere increases not only the accessibility but also the processing of this data and the referencing of this data. Having it just being published or in a manuscript as a PhD student is really great, but including it in something like a base map where it's fully accessible, that we can, you know, when you're using Google Maps or Bing Maps or Facebook Maps, you're seeing a person's farm and you know it's there, is demonstrably different. I don't really know how to put words to that, where in terms of actually scrolling around in Google Maps or Apple Maps and or Bing Maps or Facebook Maps, Snapchat, whatever maps, and seeing absolutely nothing in the middle of Nebraska or huge areas of Nebraska, in my mind is unacceptable. Because there is something, it puts something there that's actually there. There's no reason why a business deserves to be on the map, but a farmer's business doesn't. That's at the end of the day, in my view, and I hope in my mind it provides people some sort of spatial representation. I don't know.
Yeah.
Do you think that farmers would perceive it as like an invasion of their privacy since they're private landowners? I'm like trying to think about this in my head as I think about, well, like, yeah, my property is on a map, on a Google map, like you can see my house, but you can't see what I'm doing with the rest of my property.
Yeah.
So how do you think that these landowners will receive this information from you saying like, I want to put your farms and like, how are you using your land on maps?
Well, I don't, honestly, I don't think they'll react well. Which is unfortunate, but what I would also say is, when you look at a farm, I should have pulled it up, but I just pulled up Hot OSM in case anybody wants to explore. It mostly just looks like a greenly drawn boundary. There are some, very few number in the hundreds of fields that are drawn in the state of Nebraska out of the hundreds of actually over 1 million farm fields in the state of Nebraska. There are some drawn, very, very, very few number. So it's just, in my mind, it's so benign, where all you're seeing is a outline of their field in turquoise green or lime green or whatever, that they would react more angrily over the Google Street View driving past their house and capturing their number of cars and what their house looks like, rather than some guy just drawing a plot of land that they happen to own. I don't know, I like to think they would approach it with some reason, but I know a lot of times with these types of data sets, they are the way they are because of the general outcry from this community. But I do think that this is, it's literally just a green rectangle on a map, you know. In Dodge County, you can click on their fields and view how much they're paying in taxes and how much their field's worth. It was a sharp rectangle. So, like, you know, I would hope that, you know, people would approach it as a sense of visibility. I don't know. It's a great question.
I guess how much detail would you be going into when like you delineate those like farm plots? Would it be just like, oh, they're growing corn or soybean, or would you go into like they're using this type of tillage or they're not tilling or?
So we've actually started doing this. It's literally just a rectangle. It doesn't even say farm. It doesn't say who owns it. It literally just a rectangle, and usually it'll have like a crop symbol on it, not corresponding to the crop. That's it. That's all it's doing is providing a spatial bounding. There's no metadata attached to it. There's no names, PI information, or yield or anything like that. That portfolio itself is a academic pursuit that's really only available for the NRCS and the publications that occur or may not occur. Yeah.
Any more questions? All right, awesome.
Thank you.
Yeah, if everyone can thank Noah. And then on your way out, just make sure you signed in on that sign up sheet out there. And yeah, I'm Bailey Fiddle if you have any questions about any of it. Thank you. We'll be back next week. Thanks everyone online.
Yeah, like you already.